Hello everyone, thank you so much for having me today. I would like to talk about introduction to ocean biogeochemical modeling. As you may already know, I'm an ocean biogeochemist, and in my research, I'm using ocean biogeochemical models as a research tools. So I would like to develop a course about introduction to a system model, focusing on ocean biogeochemistry. And the goal of my talk today is, at the end of the talk, I hope that you can have a basic understanding of what is a model and what is not, understand why we did models and what are the types of scientific questions that models can address, and when models might not be the best scientific tool. And most importantly, I would like you to have a basic idea about model thinking and philosophy. And the talk here, I'm going to focus on ocean biogeochemistry, but because that is my expertise, but it can apply, I think it can apply to any other kinds of models in the real world. And the why I focus on these goals, because I think oftentimes it happens in is that there is a miscommunication and misunderstood between models and observationalists and experimentalists. Observationalists and experimentalists often think that what we do as a model is a black box. They cannot understand what we do behind the computer screen, and treat what we do as a modeler as a black box, and it is something magic behind the computer screen, so that they don't understand it and they don't trust it. And I think it's unfortunate, and hopefully at the end of the talk here I can communicate what would be like to be a modeler to you, and it we can have a better communication between modelers and observationalists to work towards us common scientific goals. And so without further ado, I'd like to ask, what is a model? And my definition here is just my definition, but in reality, they can have we can have many definitions. So my definition is a model is any representation, conceptual, mathematical, of the real world phenomenon, process, or system. For example, in ocean biochemistry field, you go out into the field, you measure data, you go to the lab, you take some measurements, you do some experiment, you have the data about the how phytoplankton consume carbon, nitrogen, phosphorus, silica, and iron, and to produce dissolved organic matter, particularly organic matter, and how phytoplankton can be eaten up by zooplankton and transfer the carbon up the food chain. And when you want to understand the system, before analyzing the data that you have to have a have a picture, a visualization, a representation of the real world system, phenomenon, and process in your head, so that you can have a basic understanding of what you're studying, and the big picture, a clear picture of what you are trying to understand. And what I just described about the ocean biochemistry system is that is what I already forming a representation, a model, a conceptual model of the ocean biochemistry model in my head. And also, for example, when I talk about conceptual model, you can have an example. For example, like you talk about ocean biochemistry, you can have an NPZ model, NPCD model, a model about the relationship between phytoplankton, zooplankton, nutrients, phosphate, and dissolved organic matter and particles, so that you can have a visualization, a representation of ocean biochemistry model, and have a basic understanding of the relationship between different components of the ocean biochemistry work, like phytoplankton, zooplankton, nutrients, particles, and dissolved organic matter. So you have a visualization of the system in your head. Is when you form a conceptual model. And when you have a conceptual model, you have a visualization of the system in your head. You can use words to describe what you have in your head. Like, for example, if you're focusing on the primary production and the phytoplankton biomass, you can know that phytoplankton biomass is the function of the growth rate. In turn, it's a function of light, temperature, and nutrients, a function of mortality of phytoplankton, a function of predation of zooplankton on phytoplankton. And you describe the system, the visualization in your head by using words, and you translate it to mathematical equation using mathematical language. On the right hand side here is a mathematical equation that looks rather complicated, but it just what I described to you in words using mathematical language. So we have the change of phytoplankton biomass over time is a function of the growth rate, mortality rate, and the grazing of zooplankton or phytoplankton. So we have a mathematical model of the marine ecosystem to describe the visualization in your head using the language of math and to quantitatively describe the processes system of interaction. And you can solve the equation analytically by pen or paper, but sometimes the system of equations is rather complicated and it's not easy to solve it analytically, so you have to solve it numerically in a computer. What I mean by solve the equation numerically is that we transform the mathematical equation into numerical language. For example, like here, you want to know the state, the phytoplankton biomass at a certain time, t+1, you can use the phytoplankton biomass at the previous time t plus all the processes that control the phytoplankton biomass and multiply with delta t here. That is the difference between t+1 and t, so that you know the system phytoplankton biomass at t+1, and that it means to solve the equation numerically in computer and then to really apply to a computer to solve the numerical equation in computer, you have to translate the mathematical equation into a language that the computer can understand. And the process of translating the mathematical language in the equation that we see before into a computer language, it's called coding. And that's what we see here on the left hand side is the model that I'm working with every day is a computer language that describes the equation that we see before. Basically, it's rather complicated, but basically just describing, for example, the dissolved organic carbon concentration at certain time as a function of the dissolved organic carbon concentration at previous time, plus all the processes that control the dissolved organic carbon concentration in the ocean, and the computer center that hosts CPU computer to solve the system of equations numerically looks like this in the real world. All the CPUs are connected together and it hosted at a computer center. And why do we need model? I'm just going to repeat some of the things that I already said, but first, conceptual model helps us visualize the system to have a basic understanding of the relationship between processes, between different components of the system. For example, here again, looking at NPZD model, we can have a basic understanding about the relationship between phytoplankton, zooplankton, nutrients, dissolved organic matter. What happens if you increasing phytoplankton growth? What happens if zooplankton eat more phytoplankton? You can ask some simple questions and have some simple answers based on the conceptual model. And to answer the questions more in a quantitative manner, you can use mathematical model to quantitatively describe the processes and systems interest to explore the relationship between different processes in a quantitative manner and testing hypotheses in an efficient way. For example, by just looking at the change of phytoplankton biomass over time here as a function of growth rate, mortality, grazing, we can ask simple questions like what happens if the growth rate of phytoplankton increase, what happens if mortality rate increase, and what happens if the grazing of zooplankton or phytoplankton increase, and the change in phytoplankton by how much. So we can ask and answer questions in really a quantitative manner in an efficient way by using mathematical model. And you can use mathematical model and using model in general. For example, here the NPZD model as a function of that. So we can have NPZD 1D model to explain what we observe in the ocean. Here I'm looking at the observed protein profiles of phosphate, nitrate, net primary production, and chlorophyll in the Mediterranean Sea, and see if I can use NPZD 1D model to explain what we observe in observations here and know about which process is going to be the most important process that bring about what we observe in the ocean by using a very simple and efficient model NPZD 1D. And sometimes If you look at, if you are interested in large scale ocean processes or even at the global scale or processes in some regions that difficult to go to and take measurements, we have to use numerical model that looking at processes and phenomena at the local global scale or large scale basis scale, like the whole Atlantic, the whole Pacific, and the whole Indian Ocean, for example, to understand what's going on when, for example, in the Arctic, Southern Ocean, on some in some regions of the open ocean where it's difficult to go there and take measurements, and we rely on model to know what really happening in those regions, and what are the types of scientific questions the models can address. Again, I'm just gonna repeat something that I already mentioned, like hypothesis testing in an efficient way. What happens if we add, remove, or change something, or what happened in the real world ocean if we go under extreme events? We cannot do those types, answer those types of questions in the real world by going to the real world, but we can do that easily and very efficient by using model, and by changing or adding something or removing something, some processes in the model, you can have a quantitative dynamical understanding of processes that control the real world system, and what are the most important processes that controlling the system, the components of interest. And by using model, we also assessing some unknown processes and risks that are otherwise difficult to measure. For example, when you go to the ocean, it's easy to measure temperature, salinity, but sometimes, oftentimes, it's very difficult to measure chemical rates like oxidation rates, but you can rely on model to know about those processes. And one of the things that is most often talked about is prediction and forecasting what the ocean will look like at some point in the future if we keep emitting carbon dioxide, if we keep increasing the earth temperature, what did the ocean look like at some point in the past under extreme events like extinction events of volcano eruption. And finally, we can look at the results of the model. And for example, we see something interesting that happens in the Southern Ocean, or in some regions that we currently do not have data for. And maybe you can design an observing system or campaign that go to that helps us go to those regions in the future to really confirm that is it something really happening there, interesting happening there as suggested by models. And finally, I would like to talk about what is not a model, what model cannot do. So I would like to emphasize that model is a representation of the real world, but it's not the real world. It simplifies a very complex system and helps us visualize the system in our head and have a basic picture, clear picture, basic understanding of the relationship that control the system. And that's why it's useful. So I would like to bring out an analogy about the map here. When you go to a new city, you look at the map to know the direction to go to a mall, to go to a supermarket, but we wouldn't expect, and the map is not gonna include details like the trees, the houses, the turn of the road, or like some really small details about the supermarket and the malls. And it's the same for model. And that's why the model is useful, because it's giving us direction and basic understanding of the real world system. Model can not replace observations, measurements, and lab experiments. Modelers need information from observationalists and experimentalists to constrain and know which processes are important that need to be represented in the model, and how the way that we represent in the model, does it make sense or not? And without information from observations, how can we know that our model does a good job in representing the world? So we really need information from observationalists and experimentalists, and communication is really important between modelers and observationalists so that we can work together towards a common scientific goal. And model is good at providing directions like a map, giving the directions, going to the mall, going to the supermarket, but might not be so good at details like the map is not so good at giving details about really small details like trees and house next to supermarkets and malls. So often I hear criticism that how we can trust model if the model do not give us a good prediction of if it's gonna rain this afternoon or tomorrow or not. how we can trust model about information the model gives us about what happens in the next 10 years or 15 years if we keep emitting CO2, if we keep increasing temperature of the earth. I think I understand the criticism, but I don't think that is a fair criticism. Model is good at providing directions. What happens if we keep continuing to do something, but it might be not so good at like giving you the information about the weather that happens this afternoon or tomorrow. And I would like to conclude my talk with some quotations that I think useful for model thinking and philosophy. All models are wrong, of course, because they're not the real world. They're just a representation of the real world. They simplify the real world. But that's why it can be useful if we know the strengths and limitations of the model. And again, with the analogy of the map, if we have a map as big as a real world and has as much details as a real world, I think that map is going to be useless. We cannot use this map to give us a direction, a big picture, a clear picture of the direction of where we would like to go. And that's going to be the same thing for model. So with that, I would like to thank you for your attention, and I have to take any question.